Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we are happy to have you, Aram Hao from the University of Washington, and we'll talk about quantum computing, but he will hide it under injective tensor norms.
Thanks, Boaz. Yeah, I'm happy to be here. I mostly work on quantum things, and with this research, I was trying to work on a quantum problem, but stumbled into something of possible interest on normal computers, so I'm here to tell you about it. It's about these beasts called tensor norms, injective tensor norms. And so what is this about? The idea is that we want to consider tensors. You know, we've got a lot of mileage out of matrices. Tensor is sort of the 3D version of it. And since I'm at Microsoft, I thought I'd explain it in the local dialect. Hopefully explains exactly what I'm going to talk about today. That's true. I guess it's true even without Visual Basic. It's still also just true in Basic. And so what are the questions we want to ask about it? Well, all the things that we did with matrices, we'd like to also try and do with tensors. For example, matrices have rank. Can we compute the rank of a tensor? If we could, then this would, well, in the past, when we've done this, this has given rise to some of the best algorithms for fast matrix multiplication. Even for some very small, very finite size tensors, being able to compute the rank has been a very useful thing. Unfortunately, it also seems to be very hard, even over F2. This talk, I'm going to talk about norms, one particular norm, which turns out to be equivalent to a lot of other things. But there's a more general question also of just structure. So I'm going to focus on the computational issue of how hard is it to compute a norm, what problem is this equivalent to, et cetera. But the trying to find algorithms, in a sense, is a proxy for trying to find mathematical structure. Finding the largest, finding the norm, operator norm of a matrix corresponds to things that we know about it, like its singular value decomposition and its eigenvalues. I'm not going to directly get into issues of the structure of tensors, but sort of implicit in trying to find out the algorithmic properties is trying to find out things about the structure of these beasts. So the main norm I'm going to focus on is this injective tensor norm. And the formula looks a little like a beast, but I'll try and explain why it should be intuitive. So T is this tensor that has indices I, j, k. And the norm is the maximum over all unit vectors, x, y, z. And I've taken them to be complex. You can imagine this all over reals just as well. Because it's complex, I need the absolute value here. And it's just this sum. Basically, you can think of T as a trilinear form, if you like. And just what's the largest value this form can take on any unit vectors. So why does it have this name? It comes from the tensor product, which is kind of a key feature of tensors. If x, y, and z are vectors, n-dimensional vectors, their tensor product is the n-cubed dimensional vector that you get by taking all possible triples of entries and multiplying them together. So this is indexed by I, j, and k, and that entry is just the product of the ith entry from x, the jth entry from y, and the kth entry from z. Yeah?
So the vectors are unit with respect to the L2 norm?
Yes. Yeah, unit vectors with respect to L2. Thanks. So the tensor norm arises naturally from the tensor product, even in a more abstract setting. So one way to look at it in terms of the tensor product, this is an arguably simpler formulation, it's just a maximum over unit vectors of the inner product of T, now viewed as an n-cubed dimensional vector, with this tensor product, x tensor y tensor z. And why do I call it injective? I don't fully know why this word is used, but what property it labels is the following. Imagine, so now in a more abstract setting, whenever I talk about vectors, individual vectors, I'm going to talk about their L2 norm. But you could imagine just some general Banach space where there's some norm on the individual systems, and you tensor them together, and you want to define a norm on the composite space. And one property you'd like for this norm would be that the norm of a tensor product should equal the product of the individual norms. But once you've specified that, you still have a lot of freedom. And there's a whole class of norms you can choose. And it turns out that there's a norm which is smaller, which is minimal. For any vectors, it's smaller than, this norm is smaller than any other norm. There's another norm which is maximal. And the minimal norm turns out to be this injective tensor norm. And the maximal norm is called the projective norm. It's the largest thing consistent with the triangle inequality, which is not too hard to figure out what it is. And it turns out to be the dual to this norm. So this is
smallest means point-wise smaller?
Point-wise small. So it doesn't have to, such a thing didn't have to exist. But it turned out to.
So what does the projective norm project onto?
I don't know. And I don't know what this injects into either. I don't know why they call it injective and projective.
There's an injective and projective limit in the category.
Oh.
It's not projecting in the sense of mixed space projecting. It's
right. So so other norms in the middle, for example, would be you could just take the ordinary L2 norm of this thing, right? And that'd be in between the two things. For matrices, the injective norm is, of course, the operator norm, and the projective norm is the nuclear norm, the Schatten 1 norm, sum of the singular values, whatever you like. OK, so these are our tensors. Now, a couple months ago, you had Santosh Vempala speak here about tensors, and he gave an application which I want to also mention, which is this problem where you have. So here I have a graph where I've chosen half the edges present, half the edges not present randomly, except I've also chosen 6 vertices and put edges in between all of them. Does anyone want to say what the 6 vertices are? Yeah, I mean, it's sort of, you can tell, I mean, the average degree is 7, right? And so by adding this clique of size 6, I've really moved it by a ton. But still, not super obvious. 3 is in the clique, and its degree is really low. Takes a little while to see it. So 15 is sort of about the limit. It starts to get tricky after that. So what exactly does this problem look like? Well, the largest clique, if there's nothing planted, will be size 2 log n. This gn 1/2 means half the edges are randomly present. If you just start picking the highest degree vertex and choosing its neighbors, you get a clique of size log n. If you plant a really big clique, like I did, then you should be able to find it by just examining degrees. So the degrees are have variance, standard deviation of root n. So if the clique size is this much bigger, then just by looking at degree distribution, it'll be very noticeable. And then with a more sophisticated argument, you can look at the adjacency matrix, look at its eigenvectors, and then if the clique size is more than roughly root n, constant times root n, then you should be able to find it. So planted clique means you take a graph, a gn 1/2 graph, where half the edges are present randomly, and then just superimpose on it a clique. So I guess it wasn't obvious from that example which ones were the random edges and which were the planted. But right. So that's so anywhere. So the question is, how large of a clique can we find? And anything smaller than root n, we don't really know how hard it is to find it. We know that it can't be that hard because in time n to the log n, you can just do an exhaustive search for a clique of size 2 log n plus 1. And if you found it, then you're probably outside of the, then you must have found something artificial. And then once you've found part of it, you can keep on growing it.
Can you explain the point number 3 about why that's the critical size?
Yeah, because the degree distribution of a graph would be binomial distribute. Each degree has vertex is binomial distributed degree. So probably it'll have n over 2 plus or minus order root n. And the chance that it'll have k standard deviations more, so k root n higher degree than average, will be like e to the minus k squared. So there'll probably be
square root of log n is the maximal.
Exactly. So there'll probably be on average, there'll be one vertex with degree this much higher than average. And so, if you have a bunch of those vertices, then it becomes suspicious. Or if you have one that's much more than that. Right. So this problem can be solved in time n to the log n. So it's probably, it can't be that hard. Yet we've been kind of stumped on moving past there. One approach was proposed by, I think, Fries and Kanan, and then improved by a series of other papers. And they actually propose a slightly more complicated tensor, but this gives you the idea. They propose the following tensor. A is the adjacency matrix. The ijk entry is the parity of the number of edges between I, j, and k. How does this work? So the tricky part is to show that if there's no clique, then the injective tensor norm is roughly root n. To see why this is roughly the right answer, if you try plugging into this, pick x, y, and z to be random plus minus 1 vectors. And then you get that the resulting quantity will be roughly plus or minus root n. So random vectors achieve more or less this. And then by careful concentration of measure arguments, you can argue that, in fact, no vectors do better than random vectors. This is for a random graph, right? So if there's no clique, but it's a random graph. Yeah, so if you can also talk about planted clique in non-random graphs, and that's a different story. OK, so what if there is a clique? This is the easy direction. Then the vectors you pick are proportional to the indicator vectors for that clique. And so you'll have sort of s by s by s of all minus 1s. Everything, all the signs pointing in the same direction. Neglecting the terms where some of the things equal. So that'll be s cubed, and then the normalization will be over the square root of s cubed. So you'll get a contribution the clique will give you a value of s to the 3/2. Maybe you can do better with another vector, but this gives you that the norm is at least s to the 3/2. So when s is bigger than cube root of n, this gives you a viable algorithm. At least if you can compute this norm, then this will be a way of finding cliques. Then this norm will be able to distinguish cliques. And so this was proposed originally when people didn't know so much about how hard it was to compute this norm. You could think of it as, if you believe that computing this norm is hard, you can think of it as a hardness result for finding a clique.
The opposite.
But they hoped that If you believe planted clique is hard, this is a hardness result for the tensor problem. Or if you believe the tensor problem is easy, then this gives a new algorithm for the clique. And from the tone of those papers, it seemed it was more the latter, that people were on the optimistic side. So I guess today I'll report some more pessimism, I guess. OK, so to understand, though, what's going on with these norms, I think it's better than at first, instead of talking about what can be reduced to what, I think it's more instructive to look at what it's equivalent to, because then we can really see that this thing is, it can put this in context better. So there's a number of things. One thing I actually talked about briefly on Monday, it's the problem of if you have a map from a vector space to a matrix, to a space of matrices, and you want to know the L2 to operator norm distortion. In other words, think of T as a map from a vector x to this matrix, where the jk coordinates give you the entries of the matrix, you want to know how much if x is a unit vector in L2, how large can the operator norm of the output be? If this is low distortion, then these will always be kind of low. They'll be always sort of constant. But if it's high distortion, then it'll be sort of maybe low sometimes, and then sometimes very high. And so if the distortion is the maximum of the operator norm of tx over all x's with all unit vectors, then this is precisely the same norm, because what is the operator norm is just taking this matrix right here and hitting it with other optimally chosen unit vectors, y and z. And so this just gives you back this same maximization. So it's not a reduction. It's really it's exactly the same problem, just recast into different terms. There's another equivalent problem, which before I tell you what the problem is, I want to give you an analogy. So this injective tensor norm, it's sort of analogous to operator norm. And for that, you're hitting the matrix with a vector, different vectors on the left and right side. And that's because the matrix is not necessarily symmetric or Hermitian. It doesn't necessarily have eigenvalues. You're not looking for the largest eigenvalue. You're looking for the largest singular value. But you can get to the largest eigenvalue by, if it's real, taking A transpose A, or it's complex, doing A star A. So how does that work? The analogous matrix thing is we want to compute the largest, the maximum this inner product can be over all unit vectors. And this is equivalent to the largest eigenvalue of m star m. And if we further rephrase it, we can rephrase this as a convex optimization problem. So x star is x is a unit vector. Xx star is a rank 1 projector. Capital X is the convex hull of all of these. And these are the set of matrices that have trace 1 and are positive semi-definite. And so the operator norm you can interpret as the maximum over this convex set of the inner product of this star with an element x from the set, where inner product is this matrix inner product, which is you multiply them together and take the trace. So that's nothing really new, and it shouldn't be surprising that we can do the same thing with tensors. So what do we get here? So we want to maximize. This is our same quantity. I've squared it because it's by this analogy, and we can write this as the maximum. Now we drop the z, a maximum over x and y, of the trace of some matrix M times xx star tensor yy star, where M is this quantity that's sort of analogous to t star t. So M is a positive semi-definite matrix. And in fact, that's fully general. For any positive semi-definite matrix, there exists a corresponding t, just like in the matrix case. And computing this quantity is precisely equivalent to computing the original injective norm. So this gives us a second reformulation, which is as a convex optimization problem. And this, if you're familiar with quantum, maybe explains how I got connected to it. So the square of the original norm is the maximum trace of m times w, where m is this other matrix, sort of almost uniquely corresponding to t. And w ranges over this convex hull of all of these matrices, xx star, tensor yy star. In quantum, these individual matrices correspond to pure product states, and their convex hull corresponds to what are called separable states, by contrast with entangled states. So entangled states are these things that exhibit surprising quantum correlations, and separable states are basically the set of everything that doesn't. Yeah?
Coming a little too quick, so let me slow you down. Is it OK to think reals throughout this page, or does it make a big difference?
Yeah, so you can think reals. Star means transpose complex conjugate. Okay. So if T happened to be a real matrix, then everywhere there was a star would be transposed, and everything would work totally fine.
All these maxima will be achieved over real vectors, for example.
Yes, because the M you get, for example, M isn't some arbitrary real matrix. It's a positive semi-definite matrix. So it's, it's the nice kind of real matrix. Yeah, so every aspect of this also makes sense over reals. So the strange,
Does it have to be a square matrix, right? The M, the top part is not square.
Yeah, so maybe I shouldn't have used the same M. So this M is not square. This M is square. And the thing about the entries of this M, I wrote I1, I2, comma, J1, J2. So the row, I get rows and columns mixed up, but let's call this one. The row is indexed by I1, I2, and the column is indexed by J1, J2. So it's a, it's a perfectly ordinary matrix of dimension n squared by n squared. And but it's convenient to sort of remember the tensor product structure there that it came from. That sort of the first index still kind of corresponds to x, the second index still kind of corresponds to y, and the z index we got rid of. So in the matrix case, this set of x's is a very simple one to analyze. You can test membership easily. You can optimize over it. It's kind of the nice sort of convex set. Here, this is a simple to describe convex set, but it's kind of, it doesn't look quite so nice. If I give you a matrix and ask you to tell me if it's in the convex set, it's not obvious whether you can do that. The extreme points are, well, I guess all the points of this form are the extreme points. But it's, certainly there's an infinite number of them. And despite it being convex, it doesn't make our lives that much simpler. However, it does mean that optimizing over it is equivalent to determining membership in it. So this formulation will be useful for, will turn out to be a very useful one mathematically, even if it, because it's equivalent, hasn't made it any easier to compute.
So the extreme points are identifiable, etc., but it's the convex set, it's not.
Yeah, and the problem is the extreme points are identifiable. They're these guys. And so if you want to maximize trace of m times w, where w is in the set, all you have to do is maximize w over the extreme points, and you're back where you started. So that's the difficulty, is that the extreme points are, not as nice. It's not as nice as having these extreme points where your things are just quadratic. OK, so this is another formulation which is of interest to quantum people, but also, may have other uses. There are many, many other equivalent formulations also useful for quantum, which I won't spend too much time on, but I want to briefly mention. So one of them is if you want to analyze a mean field Hamiltonian. So Hamiltonian means something that takes a state and tells you what the energy of the state is. So like the state might be the configuration of a lot of little magnets, and the Hamiltonian would say the energy is high if adjacent magnets disagree, and it's low if adjacent magnets agree. And these things are often hard to solve, so one approximation that people make is they say, well, instead of saying that a particle interacts with its neighbors, just assume that every particle interacts with every other particle in the system equally. And this sounds like kind of a silly approximation, but it actually gives some reasonable results. Like the Curie law for magnetism that really predicts how a lot of magnets work is based on this approximation. It's called the mean field approximation because you assume that each particle interacts with sort of the mean field of all the other particles. And it turns out, if you want to solve such a Hamiltonian, then you look at the two-particle interaction, and you optimize that over all separable states. And so finding the lowest energy of that is precisely equivalent to that problem, the same injective tensor norm problem.
Solving a Hamiltonian is to find the minimum energy configuration?
Yes. So the only difference, so it's exactly the same except minimum instead of maximum. So yeah, minimum energy configuration because we assume that systems like to inhabit the lowest energy configuration at low temperature. So physicists had observed kind of in doing their numerics that when they would try and solve these mean field problems, things would be numerically unstable. But there wasn't, there was no systematic explanation of why that was true. It just was folklore considered to be an annoying problem. Another problem that I briefly mentioned is that we want to know whether a quantum state is entangled. So what that means is, if you have a matrix, does it belong to SEP or not? That's basically all that it means. This comes up in practice. People make a state in the lab and want to claim that they did a successful experiment to create entanglement. If the state's very small, it's easy to check. But if you have completely determined the coefficients of the state numerically, experimentally, and then you want to plug into a computer and find out if it's entangled, it might still be a tough problem. This is what I mean by weak membership. This is you're given something which you're promised is either within the convex set or epsilon away from it, for example, is an example of a problem you might want to solve. And it's not obvious, but you can show that this is equivalent to maximizing a linear function over this convex set, up to some change in the epsilons. And so this is, again, equally hard. Another problem which is equivalent, it relates to quantum information theory. We often want to know if we have a noisy communication channel, what is the least amount of noise possible to achieve in the channel for some choice of input. So it could be that every input you put in has the same entropy at the other end, but it could also be that some inputs have lower output entropy than others, and you want to find the input with the least output entropy. Outputs correspond to matrices, and more noise corresponds to having lower largest eigenvalue. So again, this is equivalent to the first problem I mentioned of finding the lowest distortion. And there's one more connection I'll mention, which I actually just learned about a few days ago, which people here, Boaz and other people here, are working on, is calculating the L2 to L4 norm of a matrix. So you have a matrix A, and you want to maximize the 4 norm of the resulting output over unit vector inputs. And so if you unroll this 4 norm, you get something which is quadratic in X, right? And then so it's XX star tensor XX star times some matrix M, which comes from A. It's not very hard to write it out. And this looks almost the same. The only difference is it's XX star tensor XX star instead of XX star tensor YY star. So this maximum basically constrains X and Y to be equal. In general, those quantities can be different. In this case, it turns out that the extra freedom doesn't help you because of how symmetric M is. And so again, you get the same problem. So this, of course, for a specific choice of M.
Because M came from A in some specific way.
Because M came from A in a specific way, right? It won't always be true. So there are more examples I could give, but basically, whenever you want to do something where there's a bit of nonlinearity and you want to maximize, it's going to look pretty close to this. The one thing you might notice is that it's sort of only one. So here, this is, if this were a 2 instead, this would be the usual eigenvalue problem. And so the fact that it's a 4 is just like slightly higher degree than the usual eigenvalue problem. And so one thing that's been consistent through these examples is that we haven't increased the degree by very much, which is, you might look like a bit of a limitation. It might look like, OK, well, at degree 3, you get some things. At degree 5, you get some other things. And it might look like, even though there's some similarities here, there won't be a very general theory. It turns out that this can be unified even with higher degree things as well, which I'll get to in a minute. So
the fact that it equals is just Cauchy-Schwarz, right?
Here, you mean?
Yes. Because I think it just as a 2-dimensional vector of AX tensor AX, and then I have the other 2-dimensional vector
AY, tensor AY, and I use and this is the scalar product of those, and I use Cauchy-Schwarz to bound it by.
Yes, yes, that's right. So that's yeah. So, and that in turn is possible because this M is not fully general. But that's right. Okay. So how? So before I talk about higher tensors, we should review what has been known about this in the past. Yeah.
So are you really claiming now that AX, the fourth norm maximization, is equivalent to computing the injective tensor norm, or it's reducing?
So I haven't shown you the reduction in the other direction. I haven't shown that if you can do this, then you can calculate the tensor norm. Nor do I fully know that, actually. So I know that the restriction that x, if you require x's to be the same, if you require x equal y, you can simulate the case where x is not equal to y, because you can change your vector to the form, x concatenated with y. But that is for general M, and the question is, can you simulate general M with an M of this form? I believe it should be possible, but we haven't thought about it that much. So in that sense, I'm cheating a little bit because I did claim it was equivalent, and this is a bit of a reduction. The others really are equivalent if you're allowed to vary overall channels, all Hamiltonians, and so on. Okay, so I want to say a little bit of what we know about hardness for these things, because we're not totally in the wilderness. And I'm going to, even though I introduce things with this injective tensor norm, I want to, to make things more quantitative, it's a little bit nicer to talk about this separable norm to set the scale of things. And because M is a matrix, we can compare it to other norms in the matrix. So remember, this set SEP is the convex hull of all of these rank 1 objects. And on the one hand, we have some hardness results. So if we want to estimate this quantity up to 1 over polynomial accuracy, so to set the scale, I'm going to assume the operator norm of M is 1, or But it kind of doesn't matter. Because we're dividing by polynomial in n, this could be even as large as the trace of m, and the polynomial would be enough to wipe that out. So if you want really good accuracy, then it's NP hard to do this. There's reductions to the knapsack problem, to graph coloring, to 3 coloring, to 2 out of 4 sat. These different papers do. I left off one by Beghi as well. They all sort of, some of them improve parameters, some of them extend it to different ones of the equivalent problem, sort of tightening those connections. But they all more or less achieve this kind of hardness to do within 1 over polynomial factors.
Is this like with linear blow-up, or is it like this shows that you cannot do it in exponential? I guess if it's NP hard, it shows that you cannot do it even in a sub-exponential time.
Right, right. So you could say if you have a 3-set instance of n with n variables, how big is the matrix M? And M is, I think, I'm actually not sure if it's linear or polynomial in n. I think it's because M has these, it's inherently has this tensor product structure. So it'll certainly be polynomial, but yeah. So we know that it's hard to do it very well. On the other hand, the only algorithm was by this paper from several years ago, which runs in time n to the poly 1 over epsilon, which you can consider to be polynomial for fixed epsilon. But what you multiply epsilon is this really truly horrifying trace of m. I mean, the sum of all the eigenvalues of m. So this is really only going to be meaningful when m only has a few substantial eigenvalues. Because
so m step is would be roughly scaling with 1 eigenvalue, whereas this is the sum of all n then?
That's right. So think about M sep as sort of a crippled version of the operator norm. Operator norm, you get to sandwich M with any vector. M sep, you only get to sandwich M with vectors of this special form. But still, it's going to, in many cases, be certain. So it's upper bound of the operator norm. Often, it won't be too far away from it. Whereas, trace of M is often going to be a lot bigger. So for their applications, this was OK. But in general, this is we want to do better than this. On the other hand, this gives a limit of we can't do that much better. But there's a huge thing in the middle, which is, well, what happens if you want constant accuracy? What if you want M sep plus or minus the operator norm times some constant epsilon? How hard should that be? For most of those applications, that's what we really want. We want to estimate the energy to within 1%. We want to estimate these quantities to within some constant value. We don't need this kind of really precise scaling, and we definitely need something better than this. OK, so to get at this case of interest of when there's actually constant accuracy, I'll have to, at some point, introduce some new results, and this is what they're going to be, is we'll have to talk about reductions to the case of tensors with more indices. And so a 3-index tensor corresponds to the set of the separable states over two variables. And a k plus 1 index tensor corresponds to this set, sep k, which is the convex hull of a tensor product of k different unit vectors. And so this is, for k 2 or more, appears to have all the difficulties of k equals 2. It might be substantially more difficult to optimize over. And so our kind of main result from which a lot of other things follow is that it's not that much harder. That if you can approximate the regular separable norm, so here sep is the same as sep 2. If you can approximate this norm, then you can also approximate the k copy version of it. And so what happens with this? Sort of. Not actually for unlimited k, but there's a catch, which is, so what happens to the size of your matrix? The size of your matrix blows up by a polynomial. I mean, it more or less squares. But if you have something here, the matrices will be n to the k by n to the k. Right? And you interpret this as like a k index. Rows have k indices, columns have k indices. And then here, you interpret this as the row and columns just have 2 indices. And it turns out that your matrix will be n to the 2k by n to the 2k. So that part doesn't mind how large k is. But if k is very large, then inherently your matrices are big in the first place. They don't get smaller. This process doesn't make the number of numbers you have does not shrink. You just get to lump them together in different ways. But still, it turns out to be very useful for us that it's apart from, not shrinking the dimension. We at least don't make things worse, and we don't pay any penalty with k. So that's the reduction does one. That's the dimension. The reduction also basically has I'll just say it has constant error. It's sort of let me just be. I can go into more detail if you want, but more or less it does what you would want for constant error. So if this, for example, let's suppose that the matrix. So if you want to approximate this to within error epsilon, it suffices to approximate that to within error epsilon over 100. It's something like that. OK, so this is, I think, useful. Yeah?
Does the reduction also do something for exact computation, or does it only work for approximations? What if I can give you exactly?
No, yeah, it also works for exact. So this epsilon to epsilon over 100, that's true, for any epsilon. I mean, if you can do exact, you can also solve NP-complete problems, which include this one. So that's a more indirect way of doing it. But the reduction sort of scales nicely with epsilon all the way down. And I guess the reduction, sort of like the planted clique business, you can think of it in two ways. You can either think of it as an optimist. You can say, well, suppose, look, I know this problem is hard, but suppose I've got some good heuristic. Remember, I was talking to Pablo about this before. Maybe you have some cases where it can be addressed. You have some algorithm that sometimes does better than the worst case. That is something which is a little bit more hopeful than this, apparently much worse beast of a problem. And so this means if you develop at least a heuristic for this problem, then you can apply it to this potentially much harder problem. So I haven't actually seen this used in an algorithm yet, but it seems like it could be. On the other hand, there's the pessimistic thing, which is hardness result here translates into hardness result there. So that's the way we were able to use it. So these people proved that 3-sat with n variables reduces, and I'm suppressing some polylog here, reduces to estimating this SEP norm for the number of indices equal to root n up to some constant accuracy. So by comparison, previous work had this 1/poly. They were the first ones to do it for constant accuracy. But it was for this wacky kind of separable over root n systems, which is, arguably, it was a problem that no one had worried about the hardness of before. And it's significant because it's a sign that you can't do it in polynomial time. And what is the dimension of this thing? Well, you have root n terms. Each one has dimension log n. Actually, you have root n polylog n terms. Each one of dimension, each one of dimension n. So you've got n to the root n polylog n, and you end up with exponential in root n times some polylog terms.
That's the number of numbers you have, not dimension.
That's the number of numbers. I'm thinking of M as just a big matrix.
Okay.
Where you interpret the indices as being, root n tuples.
Number of rows and number of columns.
Yes, that's right.
So this still says that unless you get sort of a sub-exponential algorithm for 3-sat, something, right?
That's right. So let's assume 3-sat takes exponential time. Then that means that you can't solve this problem in polynomial time. And then if you just put these two together, it says you also can't solve this injective tensor norm problem in polynomial time, even to constant error. So you can reduce 3-sat to estimating the separable norm thing up to constant accuracy. And you start with a 3-sat instance with n variables, and you end with a matrix of dimension 2 to the root n times a little bit. So it's, in that sense, much weaker than the previous reductions, where the matrix just had dimension polynomial n, but it's able to achieve this better accuracy. So if you scale it down, this is maybe a nicer way of putting it. Suppose you can solve the problem, m will be operator norm less than 1, dimension n squared by n squared. You want to estimate the SEP norm up to plus or minus epsilon. This is as hard as solving a 3-sat instance of size log squared of n. So this is a test if you're paying attention. Anyone remember any similar problem from before? Yes, exactly. So what about planted clique? Well, so if I can solve the injective tensor norm problem to constant accuracy, I can solve 3-sat instance of length log squared n. I can also solve planted clique. And which should I be more impressed by my ability to solve? Well, if I can planted clique, of course, you can't reduce 3-sat to planted clique. It goes the other way around. But you can't quite reduce. So planted clique is a funny one because you'd like to say, look, I only need to search over log squared n bits, right? So I'd like to say 3-sat instance of length log squared n. But that's not true. What it is a circuit sat instance where you've got log squared n free variables. and then this poly-size circuit that makes use of them. And first I was walking around just saying that this solves a problem harder than planet Clique. And then then I sort of thought about it a little bit more and realized they really appear to be an equivalent. I don't know any reason why estimating this couldn't solve the resulting circuit sat problem. I just haven't been able to figure it out. So I can't say this is strictly harder than the thing that planted clique reduces reduces from.
But what you can say is that under the assumption that's widely believed that reset takes exponential time, then
I can say it's
this
something.
Approach.
That's right.
At least unless you somehow argue that the instances arising from planted clique are easier than usual, that this.
That's right.
Yes.
That's right. So it's certainly, if you assume exponential time hypothesis, then this is solving something at least as hard as planted clique.
The hardness was coming from planted clique, which means was a random average case hardness.
That's right.
Whereas now you have worst case hardness, right? I mean, I know that's good. So for all we know, we might be able to solve random planted cliques of that size. So
sure, right.
Yeah, we don't probably expect log squared n size at formulae.
Right. So this also, yeah. So I think this throws a little bit of cold water on the tensor planted clique link, because it says maybe this is the more a better place to focus. But of course, you could say, why log squared n? I mean, why not n? I mean, there's no proof that you couldn't have just as good hardness results as for the 1 over polynomial accuracy. And when we initially got this result, we were happy that it was not trivial. There wasn't just log n, but it was still, can it be improved? And so I'm starting to suspect that it's tight. And the reason is a series of coincidences. This is one coincidence. I mean, there's going to be no bulletproof evidence, but this is one coincidence. And I'll come back later to another coincidence that makes me suspect there might be something tight. Let me first give you a little hint of how the proof goes of this reduction from k to 2. So for this, I need to introduce yet another equivalent thing. So this should be interpret this norm of M as the acceptance probability of a QMA-K protocol. So this contains MA in there, which is Merlin Arthur. And it's going to have the same basic structure. Merlin wants to convince Arthur that something's true. And Arthur is going to do some test and hopefully accept a true thing with probability 2/3 and accept a false thing with probability at most 1/3. Except now everyone's quantum. That's the Q. And there's K Merlins. That's the K. And so each one will give Arthur an independent state. And those states, when you tensor product them together, will give you something in sep k. The first Merlin gives you x1, x1 star. You tensor that out. The second Merlin gives you x2, x2 star, and so on. And M turns out to be Arthur's measurement. So Arthur picks M and then measures it against that. And then the Merlin's problem is to try and convince Arthur to accept. So they want to pick their proof to maximize the trace of M times the thing from sep k. So that's precisely this thing again. So just another equivalent formulation, but at least for me, the adversarial way of thinking about it makes some of these things go a little bit better. So we're thinking about this as a multi-prover protocol. And so now what we want to do is we want to simulate QMA-K with QMA2. We want to simulate K provers with 2 provers. So what we do is each prover will send us the K unentangled proofs. Each one will send us states that they claim are product. And we'll ask them to both send the same thing. And now our problem reduces to, given 2 copies of a state, because we've got 2 provers, each one will send it, we want to certify that it is indeed in this class sep k. And there's pretty much, from there, it's a long road, but there's only one road. Because what you're doing is the states that you want, there's a bunch of valid states, and you take their linear span. In quantum, all you can do are these linear measurements. So you take their span, and that gives you a subspace to project on. So it's obvious what the strategy is. Then you just have to analyze it. And then to analyze it, you do like a long computation. And then the funny part is that in the middle of the computation, there's only, as these things go, there's a lot of Cauchy-Schwarz, and then one difficult part. And the one difficult part turns out to boil down to computing one of these injective tensor norms, which we should have realized at the time what was going on, but only months later did we. And then you have to bound this very particular tensor norm, which you can do using specialized arguments, and then you show the thing works. So this is sort of the structure. There's some ideas within it, but the main idea is this: that using two copies of something to certify that it's k-wise unentangled.
There's a classical analog of this, right? In the case of k-provers, you can replace by 2, and get roughly the same. And the protocol in any way mimicking that, or?
I don't remember that protocol.
It's actually, that one's very simple to analyze, but I'm not very sure exactly what these two states are that are coming from the two provers.
Basically, each prover sends you, so you've got k provers sending proofs, p1 through pk. And then what you do when you have two provers is each prover sends you all k proofs.
P1 to pk, P1 to pk.
Yeah. But so the classical one is a little bit different. The classical one has some consistency checking, now, the question is, could you interpret this somehow as a consistency checking? But also, that one's interactive, right?
No, typically one thinks of this as one round.
OK. But don't you send a message first to the Merlins?
Right.
Yeah.
Here there's no Merlin option, right?
Yeah. So actually, there is a nice parallel with Arthur Merlin with, and I'll say the details are in that paper. There is a nice parallel with what you might call AM2, Arthur Merlin games with two Merlins, where, so normally that's just called multiple prover interactive proof. But suppose, normally, classically, when you're interrogating two different Merlins, you can choose a correlated message to send them. But suppose you just have to send them independent messages. Or another way of saying that is, suppose the messages to the Merlins are just given by some independent, random beacon. So there'll be some beacon that sends Merlin 1 a message and Arthur, that same message. And another beacon sends a message to Merlin 2 and Arthur. These Merlins calculate something and send messages to Arthur. So it turns out this has similar strength to QMA2, at least for 3-sat purposes. So if each of the Merlins send a root n size message, that can be used to solve 3-sat. Why is that? Because you ask each one to send you a random root n size subset of the bits of a probabilistically checkable proof, and then they'll probably overlap. And then conversely, in time exponential in root n, you can simulate such a protocol. Exponential in n. Otherwise, it'd be very surprising. More generally, you can simulate the protocol in time exponential in the size of the first Merlin's message times the second Merlin's message. And this is due to Aronson and Impagliazzo. And you can ask me about it, but you could also ask them about it, and they'll tell you more. So I find that very intriguing that matches, that's the second coincidence for that log squared n, is that in this other classical scenario, they get the same, OK, so things are different in the scenario, but still they get the same root n relation to 3-sat. So our proof, so I've tried to I've neglected, even though I've said many quantum things, I've been neglecting a lot of the quantum aspects of this. Our proof has various quantum implications. for things, for quantum channels, for sort of which I won't really get into, but things about the properties of entanglement. For example, it says that if you have a multi-party state, then the average entanglement across cuts is comparable to the maximum entanglement across any cut. There's one other consequence of our proof, which I want to mention, which is not strictly related to hardness, but which people here might be interested in, which is the parallel repetition problem. So in general, if you take a matrix M, and so this part, I'm not worried about computation, just about mathematical properties of this norm. So what happens if we take many tensor powers of a matrix? Then the norm will at least raise by a power, will at least multiply, but it might increase even more. So it at least multiplies because whatever the optimal was here, you can just tensor power that up and get it optimal for the other one. But your set of possible vectors to choose from is grown, so maybe you can do something even better and increase it more. And in fact, there are examples where you can. So there's an example where the injective norm of a single matrix, this is actually one I mentioned on Monday, is a half. And if you take 2 copies of it, instead of multiplying and getting a quarter, you get almost a half. So this is really almost tight. But that's where it ends. I mean, that's where our examples end, not where the possibilities end. It could be that if you keep on tensoring more things, it can always stay really close to a half, or stay really close to half for a long time, but we don't know. On the other hand, we have this sort of weak parallel repetition theorem where if this norm is less than 1, then k copies at least go down exponentially with k, but the base of the exponent can depend rather badly on n. So we know we have sort of vague qualitative ideas of what goes on, but not much. But quantitatively, our understanding is pretty weak. One nice side effect of our proof, so we reduce an m on this k-partite m to a bipartite one. And it turns out that in the process, we also produce an m that has another nice property, which is that this equation here is an equality. So sort of for various guts of our proof, which I didn't go into, this turns out to be useful. And in fact, it makes it useful even when k is 2. It says we can take.
Such an m was not known in identities.
Oh, of course, no, that's true. Plenty of m's are known, but we produce an m for which this is true, and where the injective norm is close to the original one. So that's, that's sort of the crucial thing.
Like an m where it's hard to compute, and this is 2, or that's the point?
It's just as hard to compute as the original one. And so what this means is this lets us show hardness of various amplified versions of problems. That's why I can say it's hard to tell if the norm is less than 0.01 or greater than 0.99, stuff like that. So this solves a lot of the complexity issues related to the fact that this is not always tight, but there are plenty of non-complexity related issues about quantum information theory and so on, where we'd really like to get a better quantitative understanding of this stuff. And I would also really like to know if it relates to other parallel repetition problems. As far as I can tell, it doesn't, but likely I'm missing something. OK, so I finally want to end on this is the last part of my talk, and it's the last coincidence also, the last reason why log squared n may be, why I suspect it may be the right answer. It's a problem I really want to solve next. OK, so it starts off a little bit ugly, but I promise it's not that bad. I'm going to every time you notice m gets more conditions on it. So m is going to be between 0 and identity. That's pretty innocuous. But I'm going to further assume that m can be decomposed in this way. So I assume I can write it as the sum of tensor products of positive operators. If you remember the set SEP, it's just kind of like the set SEP, except SEP should be something that's trace 1, and m has a different normalization. But still, it's a convex combination of tensor products of positive operators. So suppose I have m meeting these conditions, and there's one more condition which I will sometimes impose, which is that the sum of the ai is no more than identity, where identity is just the n by n identity on the first system. OK, so let's consider this restricted case. The first thing is we prove this case is not so restricted. So our reduction, in fact, it outputs an m of this form. So a general m computing this thing is as hard as computing an m where you just don't have this last condition. You've got the other conditions. So the top 3 lines are pretty innocuous. And this recent paper by Fernando Brandao, Matthias Cristandel, and John Yard, they gave an algorithm. And this is sort of the last coincidence here. It approximates, it does exactly what we want. It approximates the separable norm to additive error epsilon in time that for epsilon constant is n to the log n, which is wonderful. Everything would be great if I just stopped talking now, except there's this condition star as well, which in quantum they call it LOCC. This means the measurement can be implemented by Alice doing some measurement, communicating the answer to Bob, and Bob does some measurement. Turns out, I'm cheating a little bit. The class is slightly bigger than this, but this gives you the idea of what it is. So that's the gap. So the good news is they're both log squared n. And they came to log squared n for totally different reasons. It's just, just another in a series of coincidences that suggests this may be the true answer. And the gap now is not in terms of parameters, but in terms of classes of m. So you've got fully general m. We can reduce that to m of this form. Then they have an algorithm when m is of this more restricted form. And then there's other work, which I haven't mentioned, by other people, that if you tack more conditions onto the m's, then you get into polynomial time. So the level at which we're trying to separate hardness from algorithms is now at the level of what these conditions are. Now, unfortunately, if we remove this condition, their proof, well, I guess kind of what you'd expect, right? If you remove this condition, it really appears that their proof is not going to extend. If you put this condition in, then the core part of our proof, where you have k provers simulated by 2 provers, I mean, I can prove that part cannot work. So you'd have to use a different technique in order to bridge the gap. It may be that a more direct technique could do it. So this is kind of I think an important question is, can we close this gap? Of course, these results, I should emphasize, there's a gap between them, but they are compatible, right? There's no reason why they couldn't coexist, and we couldn't have an algorithm with a matching hardness result, which I think would be a really nice thing. And it may be that the way to do it is not with quantum. So one strange thing about this is that the algorithm and the hardness result, I mean, you can state these without any quantum, but the proof of both of them is totally quantum. I mean, ours is, I suppose you could formulate it without quantum language, but theirs is really just, wall-to-wall quantum information theory. And it would be, I guess, of separate interest and maybe a worthwhile thing to try and prove it using different techniques that don't appear to be quantum. In particular, and maybe this is always the bias that authors have, I think that my own proof is very easy, and there's not very many ideas in it, and it's simple. And theirs is this like masterpiece of bringing in all sorts of different ideas from throughout quantum information theory. So it seems that maybe mine can't be simplified very much, but surely theirs could be simplified and done in a way that non-quantum people can more easily understand. If so, maybe you would get conditions that didn't quite have the same one. I don't know. But this is something I'd very much like to see. And let me emphasize that the best algorithm, we'd like an algorithm of this runtime for all these practical problems, and the best runtime we know is exponential in n. So really, we've got nothing more than a trivial algorithm. I really hope that we'll be able to find some way to improve it. OK, that's all. Thanks for your attention.
So in this paper of Fries and Kanan, where
Yeah.
they did a
Yeah.
planted clique with random graphs, I guess there was some idea even then that one could try to look at higher dimensional tensors.
Oh, yeah.
And what happens? I mean, so was the obstacle only? I mean, it couldn't have been that the algorithms were an obstacle, because algorithms are obstacle even to three-dimensional tensors.
Yeah, so I didn't mention that. If you consider a tensor with k indices, then you could suppose you could solve the tensor optimization problem there. Then you can find a clique of size n to the 1 over k. And the one thing I haven't checked, then with some prefactors that scale badly with k. And that's, so Fries and Kanan introduced this idea that you might use higher k. And I just cited the Brubaker-Van-Paula one. That's probably what their sort of more important technical contribution was, analyzing the higher k, and showing that it does actually scale. The prefactor you get with k is not too bad, and so on. So you could use higher k to do this, but it wouldn't. The hardness by these results wouldn't change too much.
No, but if one believes a positive result, then
Yeah.
you're saying if we get n to the 1/3 by these methods, then you're going to get all the way to n to the epsilon. Or
I'm not sure, because that would be great if that were true. What's not, the link that's missing there is, if you can solve planted clique of size n to the 1/3, it doesn't follow that you can solve the tensor optimization problem, the injective tensor norm problem.
And also, even if you could solve the tensor optimization problem,
It'd be
on the average
average.
case, the reduction might
Yeah.
not preserve that property, right?
Right.
Because we already know, in some sense, that you can't solve it in the worst case.
That you can't solve it in the worst.
You cannot solve
Yeah.
it in the worst case, and
Yeah.
and the reduction will take a random tensor, will map it into something, I don't know.
Right. Yeah. So it seems I played around with this for a little bit, trying to see, take planted clique in the worst case planted clique. Could this be equivalent to the injective tensor norm problem? Worst case it might be, but I don't know. It's definitely a lot more difficult than the other ones. I think we require some new ideas.
More questions? Think I'm again?